In this presentation, we'll be developing an approximation scheme for a two-dimensional wave equation. To begin, we might ask, what does a wave equation look like? And this is what one looks like at time t equals 0, and time progresses, it updates. We note that the two-dimensional wave equations that we consider in this presentation will be only defined on a circular boundary, or within a circular domain. Now, this specific wave equation can be defined by an analytic formula as seen here, which is basically just with some sums of sines and cosines multiplied by some Bessel functions. Now, what's interesting is that we can actually define a unique function u that's c squared, so c squared meaning that has second partials that are continuous. So if u is c squared and satisfies these conditions down here, we can define a unique function. Moreover, we can actually define this function up here in terms of this PDE, basically by setting t equals 0 in terms of this u, and then set that equal to f of x. And then if we take the first time derivative, set t equals 0, set that equal to g of x, we can actually uniquely define this analytic formula by this partial differential equation, which is quite desirable. So to recap, we can actually describe the wave equation that we visualize on the second slide either with an analytic formula or with a partial differential equation. Now, the partial differential equation is often known in practice, and we're often just interested in finding or computing the output of the wave equation at some specific x, y, t coordinates, notably where t is bounded within a finite time interval. So if this is the case, often finding the analytic formula is really difficult, so just approximating the output numerically is quite desirable, and we will end up developing such a numerical approximation scheme. So to describe the ideas behind it, we're going to notably compute values within our space-time domain, and then we're going to linearly interpolate between them. So the reason for linear interpolation is that our u is really nice. So on smaller and smaller domains, our functions u will approximate well. And also, we note that linear functions are just easy to work with. So of course, they're the choice that we would like. Also, for the choice of nodal values, we're going to consider the time domain and spatial domain separately from one another, and that's mainly because our time domain can be nicely partitioned in a uniform manner, but if we try doing a similar uniform partition for our spatial domain, we don't get really any values, nodal values on our circle, which is desirable. Also, this rectangular symmetry doesn't nicely mesh with the circular symmetry of our problem, so we're going to define our approximation scheme so that we can actually work with more arbitrary distributions of nodal points within our spatial domain. Also, just as a remark, we're going to actually be doing is computing spatial solutions at specific times t sub I, starting at t equals 0 and then going on throughout this partition up here. Now at each time t sub I, we solve this by using information of the spatial solution at previous time steps, and hence we're basically updating as we go along and continue computing spatial solutions till we get to our final time t. Now, in order to make this more rigorous, we're going to first approximate the time derivative u sub tt. The motivation for this is that we want to get rid of or approximate away the time component within our PDE, and really the only place where that showed up was within our partial differential equation, the actual equation that involved partial derivatives. So if we're able to approximate away the second time derivative in terms of just spatial solutions, then we'll be able to create a method that's less dependent on the time component, and that'll prove fruitful for us. So in order to get this approximation goal for the second time derivative, it'll turn out that forming the Taylor expansions at these two time steps, so at times t sub I, if we form these two Taylor expansions, we can then form the appropriate linear combination to get this expression, and simplification yields this. Specifically, we have the second time derivative, time t sub I, as being equal to a linear combination of the spatial solutions, notably where we know these two over here, and this one still unknown, and then you add and subtract some error terms over here. Now, these error terms will go to 0 because our h will be small and our u is well behaved. So after ignoring those, we get exactly what we want. The second time derivative is approximated with the current spatial solution and in terms of things that we already know. The issue with this expression is that at time t sub 1, we can't go back 2 time steps. So in order to circumvent this issue, we'll note that we know what u of t naught and u prime of t naught are by initial conditions. So using this added information at the first time step, we can form these two Taylor expansions, forming the appropriate linear combination, simplifying, and then ignoring the error terms. We get exactly what we want again. We get the second time derivative at time t sub 1 being equal to the spatial solution at time t sub 1 when you when you subtract some things that we already know from the initial conditions. So we have now effectively got rid ourselves of the time component, so now we focus on the spatial approximation scheme. In order to do this, our solution, we characterize our solution u at time t sub I by saying that it specifies this PDE where it's subject to 0 on the boundary. Now we note that this is basically just a rewritten form of what we had on the first few slides, and that's because we basically just encapsulated the spatial derivatives, spatial partial derivatives, by this nabla squared Laplacian operator. Now note that we don't have the other initial conditions here, and that's because what we're going to do is define this abstract function f sub I to actually be the approximation of u sub tt at time t sub I. In essence, we're defining a function f sub I to actually encode the propagate the boundary conditions by using information from previous time steps. And if we set this f sub I equal to this u sub tt up here, we get a new partial differential equation that we want to solve. And this partial differential equation should be close in an approximation to our original wave equation, because our approximation of u sub tt should be fairly good. So this will be our goal, to actually approximate this new updated form. And we're going to call this updated form our true solution. And this will be, and we're going to assume that we have a fixed time t sub I throughout the rest of this derivation. Now, in order to actually characterize u of x, y in a more compact manner, we're going to define this continuous function space of c naught k, which is basically the functions that have kth partials but are also 0 on the boundaries. And if we do this, we can finally write it out in this nice display by saying that our true solution satisfies it being in c naught squared, and also this satisfies this differential equation, this PDE. Also, we're going to assume that we know f sub I completely, and the reason why I bring this up is technically we don't know f sub I because it uses information about the current spatial solution at the current time, but we don't know that. We only know the past time steps. But it turns out that if we assume that we know the current time step within our f sub I, we don't actually change much of many of the major ideas, but it does simplify the algebra, so we do make this assumption here for simplicity. Now, we noted that within the ideas of our within how we're going to develop this approximation scheme, we're going to use linear functions to approximate our true solution u. Specifically, since we're only going to use linear functions on smaller domains, we're going to use piecewise linear functions. And moreover, since we're only considering the spatial domain, we're going to use piecewise linear functions that are defined within the usual Euclidean space R3. And these linear functions are commonly called planes, and planes are defined by 3 non-collinear nodal points. Moreover, 3 non-collinear nodal points define a plane, or define a triangle within the plane. So we actually want to triangularize our circle, because now we are able to define unique linear functions on each of these triangles by specifying the values of the linear functions at each of their vertices. So these vertices become very important, and we like to form this triangularization. Now, we're going to want to enumerate these vertices as previously described, because they both define the vertices and the linear functions that we're going to define on them. So we enumerate them, and then we say that p sub 1 up to p sub n are in D, and p sub n plus 1 up to p sub m are on the boundary. And the reason why we form this partition is because note that our that our wave equation specifically states that the function is going to be 0 on the boundary. So we don't actually have any freedom of choosing what the values of these linear functions are going to be on the boundary, because they're just going to be 0. But we do have freedom for the interior points, p sub 1 to p sub n, because they can vary. So we're going to consider these points, and for each of these p sub 1 to p sub n, we're going to define a corresponding basis function phi sub j, such that phi sub j is going to be equal to 1 at p sub j, and going to be equal to 0 at all the other all the other vertices of the triangles. Moreover, each of these phi sub j are going to be linear on each of the triangles, and this gives a visualization of one such hatted function. Now, we note that the phi sub j are in fact linearly independent from one another, specifically because they're mostly 0 at most of the vertices, and specifically the ones that are different. If we have two different basis functions, then certainly they're going to be 0, or they're going to differ quite substantially at their corresponding vertices, and hence when you form any linear combination, you're not going to be able to write one in terms of the others. So these are linearly independent, and if we form an arbitrary spanning element, we get something that looks like this. And it's not difficult to see that actually if we form the span of all these phi sub j, we in fact get exactly the set of all continuous piecewise linear functions that are linear on these on this fixed triangularization of our domain D, and this gives us basically what we desired. So we encapsulate the idea of the spanning space into this single letter V, and we note that these phi sub j in fact form a basis for our new continuous function space V. With this approximating space, we can now finally give our basic approximation goal. So after noting that this defines our true solution U, we can actually define our approximating solution U sub h in V by saying that we want it to satisfy this same partial differential equation. And in order to compute this, we might naively ask, well, why don't we just take the Riemann sum of these differences and hope that that's approximately equals 0? If it is, then our U sub h should be a good approximation of our true solution U. But this turns out to actually neglect the important notion of cancellation, which can be readily seen in the single variable sense, where, for example, sine of x, when you integrate it from negative pi to pi, you get 0, but sine of x does not approximate 0 well. So due to this cancellation, we're not going to take a direct Riemann sum, but rather invoke the variational lemma, which basically states that given a function f that's c naught k, if we multiply this given function f by an arbitrary test function g from the same continuous function space, and if this function product is always going to be 0 when you integrate over the interior of the circle, then we know that the given function f is in fact 0 on D. Now, this might seem like a complicated expression or a complicated idea, but turns out that the proof is entirely trivial. G is from the same continuous function space, so if you set g equal to f, then it turns out that you're just integrating a non-negative continuous function and setting it equal to 0. Thus, the integrand is 0, and hence the original function is 0 as well. So it turns out that this idea really isn't that complicated. So we can actually recharacterize our true solution so that we can integrate, but then not get the cancellation that was originally that was given in our naive experimentation earlier. So we basically note that this expression up here certainly always implies this integral expression down here, and moreover we get the converse from the variational lemma, so these two are equivalent, and hence we get a recharacterization of U at time t sub I. Finally, we make a comment that actually in the variational lemma, all we did was actually square the integrand, and the reason why we didn't do that was because squaring it, we lose a degree of bilinearity, which isn't desired, and moreover, we actually won't be able to apply a very useful theorem that will be seen on the next slide. Now, this theorem is readily seen, or it is readily applied to our current situation because, as previously discussed within our previous goal, what we did was basically just plug in our approximating solution U sub h into our true solution U right here. And that certainly won't be nice for this characterization because if we just plug U sub h into here, we're taking second partials of a linear function, which is 0, and hence we actually lose a lot of information. In fact, we get our U sub h, if we just find it in terms of this, it would be completely degenerate, which isn't nice. So in order to avoid this, it turns out that we can actually apply this nice theorem called the divergence theorem, which basically states that if we have nice enough f and g, we can get rid of these second partials, notably where one of these integrals is along the boundary. Also, this integral along the boundary is important to note because actually, if we have our true solution U and our arbitrary test function v, given our recharacterization, we can just multiply the v out, apply the linear of the integral to get these two expressions. On this left-hand side, we can directly apply the divergence theorem to get this expression, where we can subsequently note that this integral will vanish because v, due to the construction of our continuous function space, where v is going to be 0 along the boundary of our circle. So we can then combine these two terms and get another recharacterization of our true solution U, which notably doesn't include any second partials. Thus, we finally get our last goal, which states that we want to find U sub h in our approximating space V to satisfy this integral equation. And this is going to be quite nice for us. It's interesting to note that we actually desire strict equality right here, and note that before we just wanted it to be approximately equal to 0. So with this strict equality, we ask, well, does such a U sub h even exist? And even if such a U sub h exists, there do become questions about uniqueness and moreover how well it approximates our true solution, because we're still taking first partials of our linear function. Now, we note that actually in a more rigorous development, we do get a regular U sub h term in here because our f sub I includes the current spatial solution. But and if you include that information and you develop some more rigorous theory, it turns out that actually this expression does give you not only a nice approximation, but the approximation exists and is unique. We won't go into that here, but what is interesting is that with this last goal, we can actually get a matrix formulation of this integral a description of our definition of our approximating solution u sub h. So for this matrix equation goal, we're going to let our arbitrary v be written as a linear combination of the basis functions. Specifically, what's interesting about this is that v is uncountable. So up here we actually have an uncountable infinitude of integral equations, yet down here our arbitrary v can be written as a finite linear combination from a finite set of basis vectors. So the question becomes, can we introduce a degree of finiteness in our definition for u sub h up here? And it turns out that we'll be able to do that by just asking that this integral equation hold just for the basis functions phi sub j. Specifically, if we just ask for this integral equation to hold for the finite number of basis functions, we can actually use the linearity of the integral and gradient operator by forming an appropriate linear combination so that we can actually pull this sum into these terms and get our arbitrary v's. And after we do so, we get 5 implying 6. Moreover, we get the converse because v is arbitrary, so we can just set v equal to phi sub j. So these two are in fact equivalent to one another. Thus, we can now have a definition of our u sub h that actually only uses a finite set of integral equations. Now, to further simplify notation, we'll define these two functions, a sub I and L sub I, and where basically a sub I is just this integral over here, and the L sub I is this integral over here subtracted to the other side. Now, if we do that, we get 7 describing 5. And also a couple of other interesting points to make is that we know if we know what w and v are, we can actually compute a single or unique real number from these two functions right here, which is quite nice. Also, if we write w in this expression as a linear combination of functions from our approximating function space, we can actually use the linearity of both the gradient and integral operators to pull out a sum, and hence we know that a sub I is actually linear in its first law. So if we write u sub h as a linear combination, we can actually pull out that linear combination, which will be desirable in just a moment. So we write u sub h as a linear combination of the basis functions, and then we actually pull out that linear combination. Thus, we actually get rho j, or equation j up here corresponding to rho j down here. Thus, we actually have a one-to-one correspondence between this set of equations and this matrix equation down here, which then gives us our desire. We now have a matrix formulation of the definition of our approximating solution u sub h. And with this, we finally write out a more compact notation by saying this, by writing this matrix equation as a matrix a sub I multiplied by a xi vector, and we're equating that to an L sub I vector. Note that we actually know the a sub I matrix and the L sub I vector by the comments made on the last slide. Thus, we can finally give our approximation scheme by iterating through the time intervals, time steps, and approximating the spatial solution as we go along. So we set I equals 0 where we know u of t naught from initial conditions, and then we iterate to the next time step. At this time step, we define appropriate a sub I and L sub I functions, from which we can then compute the xi vector from this matrix equation that we just developed on the last slide. Thus, we form the appropriate linear combination of the basis functions, set that equal to our desired approximation of the true solution at time t sub I, and then we continually iterate through these steps until we get to our final time step, at which point we're done and we get exactly what we wanted. We have approximations for all the individual time steps, and then we can linearly interpolate between these if we want to find intermediate values as well. Thus, we have specified an approximation scheme, and moreover, we actually get good results from this. For example, when these are implemented in a more rigorous fashion within the open source PD computing software library called Phoenix. So if we set, for example, the initial conditions that were stated in the first form of the wave equation, so if we set the initial shape to be equal to this function and how quickly that shape is moving at time t equals 0 to this function, and then we implement this theory in Phoenix, we can actually get a good approximation of our analytic formula that we found on the second slide of our wave equation. So we get good approximations and we get exactly what was desired. So we conclude with giving some references, and we thank you for your time.